Today, we're diving into a story that has it all. Incredible precision, a deep cosmic puzzle, and a tiny, tiny particle that might just force us to rewrite our understanding of, well, everything. I mean, just think about that for a second. It sounds like something straight out of science fiction, right? But what if I told you that scientists are looking at some very real evidence that suggests there's a crack in our most fundamental theory of reality?
So to really get what this is all about, we first have to talk about the rule book that everyone thinks might be broken. For the last 50 years or so, our guide to the universe has been something called the standard model of particle physics. The best way to think of it is like the ultimate instruction manual for the cosmos. And here's the thing, it's been tested over and over and over, and it has passed with flying colors. Until, maybe, now. Okay, let's meet the star of our show, the muon. Now, you definitely know its later cousin, the electron. That's the particle that powers pretty much everything you're using to watch this. But the muon, it's a whole different beast. It's over 200 times heavier, and it's incredibly unstable. It vanishes in just millionths of a second. But that fleeting, heavy nature is exactly what makes it the perfect detective for probing the deepest laws of physics. So how in the world do you use a particle that disappears in a flash to check the universe's most important instruction manual? Well, it turns out you make it wobble. The whole goal of this massive experiment, called Muon g-2, is to measure something called the magnetic moment. But really, you can just think of it as a wobble. When you stick a muon in a magnetic field, it behaves like a tiny spinning top that's also wobbling. The speed of that wobble is exactly what scientists are trying to measure. And here's the game plan. First, you create a beam of these muons, and then you shoot them into this huge 7-meter radius ring. Inside, a super powerful magnetic field gets them all wobbling. Then, as they decay, remember they don't last long, they spit out other particles called positrons. And by counting those positrons, scientists can figure out the wobble speed with just mind-boggling accuracy. Now this is super cool. What you're looking at here isn't some artist's rendering or a computer simulation. Nope, this is the real deal. It's a heat map showing the actual beam of muons circling around inside that storage ring. That bright yellow spot right in the middle, that's where billions upon billions of muons are wobbling and giving up their secrets. So after years of incredibly hard work, the team at Fermilab produced the most precise measurement of this wobble ever made. And in doing so, they found a huge clue. The precision is just, it's hard to even wrap your head around. We're talking 0.20 parts per million. To put that in perspective, that's like measuring the length of a football field so accurately that your measurement is off by less than the width of a single human hair. You absolutely need that level of detail when you're looking for tiny, tiny cracks in our understanding of reality. And how did they pull this off? Well, basically by brute force. This new result comes from analyzing 4 times more data than they had in their last announcement. We're talking about sifting through the decay products of literally trillions of muons. It's an insane amount of data.
So this number right here, this is the golden ticket. It's the measured value of that wobble from the experiment's first few years of running. Now, on its own, it's just a number. The real magic happens when you put it side by side with what the instruction manual says it should be. And that brings us to the moment of truth. We've got the number from the experiment. We've got the number from the theory. So the big question is, do they match? And there it is. On the left, you see the prediction from the standard model, and on the right, you see the new world average from the experiments, which includes this latest result. You can see it clear as day. There's a gap. It looks tiny, I know, but in the world of particle physics, a gap like that might as well be a chasm. So how big is this gap really? Physicists measure it in something called standard deviations, or sigma for short. And this difference, it clocks in at 5 sigma. Now, why is that number so incredibly important? Because 5 sigma is the magic number. It is the absolute gold standard for claiming a discovery in particle physics. Hitting 5 sigma means the odds of this result being just a random statistical fluke, a complete accident, is about 1 in 3.5 million. This is the kind of certainty that makes scientists pop champagne. So, case closed, right? We found new physics. Awesome. Well, not so fast. Just when it seemed like the evidence was rock solid, a major twist emerged in the story. You see, the problem isn't just with the measurement anymore. It's with the instruction manual itself.
That theoretical prediction, the number we're comparing everything against, has suddenly become a huge source of debate among the smartest physicists in the world.
And this debate is coming from new, conflicting data. A supercomputer calculation from a group known as the BMW collaboration is suggesting a different value. And at the same time, a whole other experiment over in Russia called CMD3 produced data that also muddies the waters. All of a sudden, our rulebook has a few different conflicting additions. And this is where you just have to admire the scientific process. The very same scientists who made this incredible measurement are upfront about the uncertainty. In their own paper, they say, look, when you take all this new theoretical work into account, the discrepancy is probably going to get smaller. That's not a failure. It's just science doing its thing, out in the open.
So where does that leave us? Are we on the verge of a revolution, or is the theory just a bit more complicated than we realized? Right now, there's only one way to find out: get more data. This table gives you a really cool peek behind the curtain at how they build confidence. It shows the results from different data-taking periods, or runs, and you can see how incredibly consistent the numbers are. By combining them all, the scientists can shrink their uncertainty and get an even more precise final answer. And believe me, this story is far from over. The Muon g-2 team still has 3 more years of data sitting in the bank that they're poring over right now. When they're finished with all of that, their final measurement is expected to be twice as precise as it is today. That could finally be enough to settle this debate, once and for all. So whether this mysterious wobble turns out to be a real crack in the standard model or just some subtle feature we don't understand yet, one thing is absolutely for sure. We are peering into the fabric of reality with more clarity than ever before in human history. And that just leaves you wondering, what else are we about to find?